C Mechanics, and this is by me, Yusuf Bagwan. Alright, let's get into part A. So, a rubber ball of mass m is dropped from a cliff. As the ball falls, it is subject to air drag, a resistive force caused by the air. The drag force on the ball has a magnitude bv squared, where b is a constant drag coefficient and v is the instantaneous speed of the ball. The drag coefficient b is directly proportional to the cross-sectional area of the ball and the density of the air, and does not depend on the mass of the ball. As the ball falls, its speed approaches a constant value called the terminal speed. On the figure below, draw and label all the forces on the ball at some instant before it reaches terminal speed. Alright, so basically what we need to do here is just make sure that's small. So this is going to be a force drag right there, which is equal to bv squared, and this right here should be straighter, but is equal to force gravity is equal to mg. Alright, so this is part B, and it says basically state whether the magnitude of the acceleration of the ball of the mass m increases, decreases, or stays the same as it approaches terminal speed. So basically what happens is the velocity of the ball increases, which means that the drag also increases because of bv squared, and it gets to the point where basically the gravitational force and where it gets to the point where the gravitational force is almost equal to the drag force, meaning there is no acceleration, meaning that acceleration is decreasing. Also, acceleration, if you just think about it, would decrease if you're going to hit terminal velocity. For example, if you're increasing, and then suddenly you're gonna hit the peak, basically you're gonna hit a peak, and then you can't increase more than that. It's just gonna be the same. It's gonna increase, and then boom, it's just gonna be the same velocity. So that means that acceleration has to decrease for it to do that. So yeah. Alright, so this is part C of the 2000 FRQ. So basically, part C says, write but do not solve a differential equation for the instantaneous speed of the ball in terms of time t and the given quantities and fundamental constants. So basically what we need to do here is create, according to the step-by-step process that we were discussed in class, was that we first draw the free body diagram, which basically looks like this. That's the dot right there. That's the object or ball or whatever. That's force drag, and that's force gravity, or other words, mg. Alright, so that's going to be your free body diagram as we did in part A. Alright, so after that, what we're going to do is we're going to write Newton's second law and use the free body diagram to help us with that. So F equals ma equals, and it's not going to be 0 because there's acceleration here. Since it's decreasing, since acceleration is decreasing, there is deceleration, which means there's acceleration. So basically F equals ma, right? And then you do basically drag is kind of like friction in the air, which is resistance. So resistance always goes in the opposite direction of motion. So since resistance is going in the opposite direction of motion, it's going to be negative. So in this case, force gravity is going to be positive, and force force drag is going to be negative, so that's going to be BV squared. Alright, and then now what we do is we turn the acceleration into the derivative dv over dt equals mg minus bv squared. And then after this, we now have a differential equation that we can solve for by dividing m on both sides, and that's equal to dv over dt equals g minus bv squared all over, or not all over, but just bv squared over m. Basically, that's what the differential equation is going to look like. This right here. That is the differential equation. There we go. Part C. Done. Alright, so part D. Determine the terminal speed Vt in terms of the given quantities and fundamental constants. So basically, again, in these types of problems where you have to find the terminal speed or anything just related to terminal velocity, what you want to first do is draw a free body diagram, which we did in part A, and which we said was that force drag is going up, force gravity going down, and force gravity is going to be negative because force drag is going to be a friction, quote unquote, force. It's because it's a resistance force basically. So resistance is always in the opposite direction of motion, and that makes it negative. So that is why force gravity is going to be positive. At least in my case. If you want to do it in a different way, you could do it. It doesn't really matter, but it just makes more sense to me. So what we do next is F equals ma equals determine the terminal speed in terms of the given quantities, fundamental constants. Terminal speed. In terminal speed, the acceleration is going to be 0 because of it just is 0 because terminal speed means that acceleration has hit a constant, meaning that it's not accelerating anymore, meaning that there's no acceleration, so it's going to be equal to 0 since a equals 0. Alright, now what was it? So it was force drag, or no, it was mg minus bv squared. Alright, now what we do is we set them equal to each other. F equals ma equals bv squared equals mg, and then divide bv, or just to find v, I mean you would divide it by b, right? So you do F equals ma equals mg divided by b, which equals v squared. F equal, and then you just square root it. So F equals ma equals square root of mg over b equals b. That's what the terminal speed is in terms of the given quantities and fundamental constants. Basically, one way that you could just solve this is, just knowing F equals, and not knowing F equals ma, but I mean just knowing that step-by-step process that we discussed in class, where it was draw a free body diagram, then do Newton's second law, then change the acceleration, not in this case at least, but change the, since it was terminal speed, but anyway, change the acceleration into dv over dt, and just keep following the steps from there. So that would help.